time independent equation. It's now a steed, what I call a steed, right? Schrodinger time dependent equation. Here it is. Okay, so you may ask, well, why not have the basic, the foundational Hamiltonian function of time? Well, I suppose you could, but start simply. Let's just add the time-dependent part as perturbing h dashed. Start small, right? Learn to crawl before you learn to walk, kind of thing. Right, so that's our basis. We assume the non-perturbed Hamiltonian, h naught, is of the STI kind, the time-independent sort. It's the Hamiltonian we've been using in the Schrodinger equation when this term here is not there, right? It's just the basic h naught. Now, so assume, this model, assume h naught is time independent, and assume that h bar, the perturbing Hamiltonian, is time dependent. Okay? And the whole thing, when your h now is the sum of these two Hamiltonian terms, the one you start with, and your perturbing Hamiltonian, so that's your h. Okay? And that h psi is this. So this is your steed. Alright, okay, now we can start doing a bit of the math. We can actually get into the nitty-gritty a little. Let's assume that go back to the STIE, S-T-I-E. So here, in the form of a eigen equation. So here's your operator here, the UN here, they are your eigenfunctions, and the En here, your eigenvalues, energy eigenvalues, right? Now, we know from earlier chapters, these wave functions, these eigenfunctions, UN, together as a set, they form a complete orthonormal set of functions. Okay, we've done this many times now. So that means that we can take any arbitrary wave function and expand it as a weighted sum, something like this, a weighted sum of eigenfunctions. Okay, so let's do that. So our wave function now, which we assume is a function of position, the spatial parts, they've left out spin, so just keep things easy, right? We're introducing new theories, so simplest case first, right? Crawl before you walk. So, okay, so psi is now a function of position and time, right? Now, let's expand this psi, which is now just an arbitrary wave function, but a function of time. Let's expand it in terms of these eigen states here. Now these eigen states, they are eigen states from the STIE, Schrodinger time independent equation. Okay? So these eigenfunctions, energy eigenfunctions, do not depend on time. Okay? You can see that here. Look, there's only an R here. There's no T. Okay? Depend only on the position. Now, now, from earlier theory, you may remember this part, the time-dependent part, that we tend to ignore, because when we square this, to get the square of a complex number, like z, modulus of z is just a random complex number, the modulus of z squared is the same thing as z star z, okay? The z just being the conjugate of z. In other words, you switch the I to minus I. Right? Well, if you take some number which has this type of component to it, part, and you conjugate it, then you get plus I, and you multiply those two together, the plus I and minus I, and the rest is the same. They cancel. You just e to the naught, right, which is just 1. So we haven't really used this much, but in the STIE Even though in the STI, time independent, we still had this term, but it didn't make any difference to the probability densities, the things that really matter, right? That are physical and measurable. Probability densities are basic. So we tended to not focus much attention on this, but now our psi, our general wave function, is from the STI, right? Time dependent. So let's keep it in. Now these eigenfunctions here from here are time independent, so no t here. And here are our coefficients. You know, we're taking a weighted. You know, we're weighting, you know, giving a different weight to these components. So these are weighting factors. W-E-I-G-H-T. You know, weight as in heavy. Okay. So a weighted sum of these components. And we bring this in as well because there's a t there. Now, notice something different compared to the STI. These coefficients now, these weighting coefficients, in this model, as we're talking STI now, we assume that they are functions of time. Right? That's the big change between STI and STID. Okay. So these now you assume are a function of time, and these A's, they're you know, once we normalize and all that sort of stuff, these A's here become probability amplitudes, right? But they're now dependent on time. So the probability amplitudes, you know, when you square them, you get probability densities. So these are now dependent on time. So the probability densities will become time dependent. Right? So expect that to happen in the future. Now, if these things are dependent on time, well, then they become amenable to being differentiated, right, with respect to time. You can start doing things like dA by dt. You could differentiate these things because they're a function of time. So now in classical mechanics, when you differentiate something with respect to time, there's a particular convention for that differential. It's in this case it would be a dot. You have to wait to the next session, but you will see appearing in various equations these A's here with dot, you know, a heavy black dot above them. And when you see that, just think, oh, that A here has been differentiated with respect to time. So d by dt of A. Okay. So here's a basic assumption now. We're forming the weighted sum of a complete orthonormal set of Eigen States, UN, right, here. And we're bringing in this term as well from the STI, because we're talking about time now. Now this is the assumption, right? It's the basic assumption in the model, as always. And how do you know it's right? Well, usual thing, by its consequences, right? Does the theory that comes out of it, the predictions of the theory, do they match the real world, the experimental results in the lab? And okay, so next session, what will we do? In next session, we will take this psi, you know, with the two terms here that depend on time, and one that doesn't. We will plug, you know, for this psi, we've got it here, and it's here, right, and here. So we'll plug this in for psi here, and we'll get an equation, a new equation, and we will also apply perturbation theory using the lambdas, you know, the lambda squared, you know, those terms. So this chapter, you can see why this chapter follows the previous chapter. We needed the knowledge of perturbation theory of chapter 10 to be able to do this. So yeah, so expect that'll be the next session.